Hello everyone, thank you for coming. So today's talk will be mainly about the up vibration actually, and as a consequence I will show how to prove a pi2 of S2. So last week Peter explained how to construct the up vibration in homotopy type theory, and explain why this looks like to be the up vibration. So today I will give a slightly different construction of the up vibration and prove in homotopy type theory that the total space is actually the 3 sphere. And then this will give pi2 of S2. So just to recall the up vibration. So what we want to construct, it's a vibration over the 2 sphere with fiber S1 and total space S3. So this is what I want to construct to give another construction of the up vibration, and it will give a pi2 of S2. Okay, so I will first start with both definition and proposition. So a lot of what I will do will really look like what Peter did last week. Well, it's the same subject. So the first proposition is the following. Assume we have the following data. So we have a push-out diagram like this. Two vibrations.
Sorry, do you mean to complete the square with a push-out, or do you just mean a span like that?
I suppose I have a push-out diagram. I have a diagram like this.
You're calling such a diagram a push-out diagram?
Yes. Yes. Then I can add the push-out and yes, the input to push-out diagram.
Good.
Yes.
Just trying to understand. Okay.
Yeah. Yes, a span. Then I assume I have two vibrations over A and B. So I have my EA. So the thought is to say that this is the total space of this vibration. So I have a vibration over A, a vibration over B, and then I can pull back the vibration over A. I can pull the vibration back along F. So I get some F star of EA. And I can pull this vibration back along G. I get some G star of EB. And now I will assume that, so I get two vibration over C, and I will assume that I have an equivalence between the two. Assume I have an identification of the two vibrations, F star of EA G star of EB.
What is
Yes?
the notation you use for the pullback vibration?
F star, upper star of that. Okay, now if I have everything like that, the idea is that we will be able to construct a vibration over the push out of this diagram. So then we can construct a vibration E so this is the push out of the diagram. And I said that we can construct a vibration over this diagram, over this object, such that okay, so here I have the push out with the two canonical maps. So now we have a vibration over the push out, and I have to say that it will respect the data I have. So when you pull this vibration back along I, what you get is a vibration over A. And the condition is that this vibration is equal to the vibration EA we started with. And similarly, J star of HoTT is equal to EB. And finally, the upper square commutes. So we have a square. Commute. So there are two parts to this proposition. The first part is we can construct a vibration with these properties. And the second part is that, moreover, this diagram is actually a push-out, homotopy push-out. Okay.
Sorry,
Yes?
can I just ask, the setting we're working in, are we assuming a classical topological setting or the type theory or a more abstract setting?
Well, we are assuming a homotopy type theory, but the same kind of, well, for the proof I will use a type theory. But I guess the same statement, well, the statement is purely homotopy theoretic, so it should work in any kind of homotopy category where you have this kind of constructions.
So for instance, when you say you have a vibration over A, you say actually it's a map from A to type?
Yes.
Yeah.
Yes. For the proof, I will interpret vibration over A by a map from A to type.
And so when
Yes, but well, you can say it commute fiber-wise or it commute on the total space. It will be the same type theoretically.
And the push-outs are all homotopy push-outs?
Yes, yes,
In the sense that you defined in your previous lecture?
yes, and I will define it in the proof. So yep.
You have not been using the maps, the inclusion maps from A into, oh, you do?
Yes, yes.
Oh, okay.
I said the vibration over the push out. If I pull back along I,
okay,
I get EA.
Okay, missed the diagram. Okay, thank you.
Okay, so this proposition basically explains how to construct a vibration over a push out, a homotopy push out. It says to construct a vibration over a homotopy push out, A, C, and B, you just need to construct a vibration over A, a vibration over B, and an identification of the two resulting vibration over C. And you get the same. And if you have such a vibration, you can recover EA, EB, and this identification thanks to this diagram. And then the second part of the theorem explains, moreover, what is the total space of this vibration. So this is how I will construct the up vibration, because the up vibration will be a vibration over S2. So the first part of the proposition will tell me how to construct a vibration over S2. And the second part will tell me what is the total space. And I will use that to prove that the total space is S3. Okay, so now I will prove this proposition, and I will switch to type theory. I will interpret everything as in type theory. So first, what is the homotopy push-out? The homotopy push-out will be a higher inductive type with 3 constructors. So the homotopy push-out has a map from A, a map from B. You have first A, you have B, and for every point in C, here if you have C, you have f of C, which is a point in A. You have g of C, which is a point in B, and you will add a path between f of C and g of C. So the homotopy push-out, you have A, B, and for every point of C, a path between f of C and g of C. The map A and J are exactly the maps here, and the fact that the diagram commutes is exactly this P, basically. Now, how do we interpret vibrations? In type theory, a vibration is just a map from A to the universe. So my EA will be a map from A to type, the type of all types. And similarly, EB will be the B to type. Okay? Now, what is the pullback? This F star of EA, the pullback of EA by F, is a vibration over C. In type theory, pullback is just a substitution. So it will be the map which sends C to EA of F of C. So the idea is that the fiber of this F star of EA over some point little c is exactly the fiber of EA above f of C. And this is how you define the f star EA. It's EA composed with f, yes.
So f star EA is just a name for a function, or?
Yeah, f star EA is a dependent type over C, defined in this way.
It's the name of the dependent type.
Yes, yes. In the same way, G star of EA of EB, sorry, EB of G of C. So now I had an identification, an equivalence between f star EA and G star EB. So what is an equivalence between two fibrations? It's a fiber-wise equivalence. It's for every point in C an equivalence between the two fibers. So it will be exactly for all little c in big C. And we unfold the definition. We have an equivalence between EA of f of C and EB of G of C.
I don't see anything, sorry.
Sorry?
It's too small.
Okay. Okay, so I assume that I have this EA, this EB, and something, I can call it E of this type. These are my assumptions. And now I need to construct the fibration E.